Hi all, this is Mr. Yeager for Honors Chem, and we are looking at percent yield today. So we've already looked at stoichiometry, how to do those calculations. This just basically adds, again, another extra step to it. So one step of it is the stoichiometry part, and then the rest of it is actually just generally a quick calculation of percentage, but there can be some modifications with it. So this is fairly quick, okay? When we do stoichiometry, you are always getting what's called the theoretical yield. All right. So this is again what we should be producing. So when we do the math, when I'm sitting here going, okay, I want this reaction to occur, how much should I get? This is what I'm expecting. The thing is, then you do the actual experiment, and you will get. That's what we refer to as the actual yield, or the amount that you actually produce. Okay. I mean, there's no other really way to say it. It's what's actually happening. So these two are clearly almost always different. I mean, I'd say 99.9% of the time, you're not going to get 100% yield. All right. There are possible labs where you might do where you can get above 100% yield, which means there's probably some contamination that you didn't eliminate. But generally, we're going to see that you have obviously less than 100% yield. So the actual calculation is percent yield equals the actual yield divided by the theoretical yield times 100. And these yields are always in mass. So in the end, we have to use the stoichiometry to get us to mass. So really, from there, it's me just showing you some problems here so you can see how this is essentially done. Okay. So it looks like a regular stoichiometry problem. This one's being nice to kind of separate it out to help you understand how this kind of goes. So it says you have sodium metal reacts with nitrogen gas to produce solid sodium nitride. Sodium reacts 6.7 grams of sodium metal in excess nitrogen. So we're trying to see how much sodium nitride should form. That's the theoretical yield, how much should form. So if I balance this out, I'm going to need to put a 2 over here because I could put a 3 at the beginning, but I have 2 N's, so I need a 2, and I have 6 NAs and 6 NAs. So what I need to do is I now need to do mass to mass stoichiometry to determine how much sodium nitride I believe I should get. So that would be 6.7 grams of sodium, and I need to change to moles. I need to go from grams to moles of sodium because I cannot change compounds unless I get to the mole ratio. So sodium is basically 23 grams in 1 mole. And then I use the mole ratio. I'm going from moles of Na and going to moles of Na3N. And so the coefficients are 2 in front of Na3N and 6 in front of Na. So at this point, if I stop the calculation, I would be able to calculate the moles of Na3N that I'm producing, that I should produce. But I want to find mass, so I'm going to change back from moles of Na3N into mass of Na3N, and the mass of Na3N is basically 83 grams. Okay. If I then calculate 6.7 times 2 times 83 divided by 23 divided by 6, I get, and this is kind of weird, this is a good example of that, 9.3 grams. Okay, 9.3 grams in the end. All right. So that's how much I believe I should get. Okay, that's how, oh, sorry, I messed that up. Struggling a little bit. 8.1 grams, 8.1 grams, 8.1 grams. I was looking at the wrong number on my paper. I get 8.1 grams. So this is how much I should produce. The thing is, the problem says you made 9.3 grams. So if I do my percent yield is actual over theoretical times 100. So I'm going to do that. My actual yield was 9.3 divided by 8.1 times 100. What do I get here? I get 115%. Now, that's not necessarily wrong. I think some people are going to go, wait, they got above 100%. That can't be right. No, it is. It happens. It does happen. It's not something that's really, that uncommon that you get a higher percent yield than you expect. That probably means you left some of the reactants are still in there. You didn't isolate your product. All right, and so that's where we get this 115%. So just be aware of that. This is a good example to kind of show, because I think a lot of people think it's going to be smaller over bigger number, and that's just not true in this particular problem. Okay? So there's an example of doing percent yield. You do your stoichiometry, and then you do your percent yield calculation. Okay? So I have one more to show. This one is talking about the Haber process, where you make ammonia, basically fertilizer. So let's talk about that. It's the conversion of nitrogen and hydrogen into ammonia. So that's N2 plus H2 producing NH3. If I balance this out, 2 N's, 6 H's, 6 H's. All right, but this one's a little bit different. It says, if you must produce 700 grams, we have to produce, 700 grams, okay? What mass of nitrogen should you use in the reaction, assuming that the percent yield of this reaction is 70%? So this is an interesting question, okay? We have our percent yield. Our percent yield is 70%, okay? The 700 grams is what we have to make. So this is my actual mass, That's how much I have to try to make, all right? The thing is, this reaction is only 70% good. So what we need to think about is go, well, if 700 grams is 70% of what should be produced, how much should be produced? So I can basically go back and look at this and go 0.7, I'm going to change it to a decimal, that's 70%, equals 700 divided by x, okay? 700 divided by x, what would that end up being? Okay, well, if you rearrange it, x will equal 1,000 grams, all right? 700 is 70% of 1,000. I hope everybody sees that okay. All right, it'd be 700 divided by 0.7, which would be 1,000. All right, so I actually need to produce 1,000 grams of ammonia. So that's what I'm going to start with, because I'm trying to go back and go, I need to produce 1,000 grams of ammonia. How much nitrogen should I use? This is how much I should produce, but it's going to only come out to 70%, so it's going to be 700 grams in the end. It's kind of weird. It's kind of a weird circular thinking with it. All right. So I'm going to start with 1,000 grams of NH3 and convert back to N2. So this is 17 grams of NH3, 1 mole of NH3. I'm going to come from moles of NH3, go 2 moles of nitrogen. So this is 2 for NH3 and 1 for nitrogen. And then 1 mole of nitrogen is essentially 28 grams per mole. So what does that all equal in the end? That will equal, sorry, I'm looking at it right there, 824 grams of N2. That is my answer. So what does this mean? It means if I react 824 grams of N2 with plenty of H2, so that we're not worried about the H2, there's plenty in there, I should produce 1,000 grams of NH3. The thing is, this reaction is only 70% yield, so instead of getting 1,000, I'm going to get a 70% of 1,000, which is 700 grams, and that is my answer with it. Okay? So that is percent yield. Percent yield, again, main things, if I just go back over here to my slide, all right, is again, just make sure you understand the difference between actual and theoretical. Theoretical is what we actually are solving for in stoichiometry, what should be produced, and then we plug it into our percent yield formula. Be aware we might mess around and kind of switch things up a little bit like we did in that last problem, where you're not always solving for the percent yield. Maybe you're solving for the actual yield. Maybe I give you a percentage and I say you have this much nitrogen, how much will actually get produced, all right? So you multiply the percent yield times the theoretical. But just be prepared for anything that might come up in regard to it. All right, that's about it. Thanks.